Hi, this is Adam Wise, application scientist in Andor in the US, and today I want to talk briefly about binning with a CCD. This is specifically an EMCCD, an iXon Life 897. So what I'm saying it will certainly be applicable to another Andor CCD you have, but the GUI might look a bit different. So first things first, let me look at my normal image here. So I'm right now reading out the entire image from the sensor. Each pixel is getting digitized, and I'm viewing it as a 2D image. So I can click around on here and I can see the values for each pixel. The X coordinate shows up here, the Y coordinate shows up here, and the data, which is the number of electrons in that pixel, is here. So it's 587. So that's the number of counts in that pixel, which corresponds to the number of electrons read out during the digitization process. So right now I could visualize this data as a 2D mode. So let me go up here and click 2D. And now what I'm going to see is a series of cross sections. So these are X cross sections across the sensor. And this is a 512 by 512 sensor, so I have 512 of these. And you can see as I change this, it's going to show the Y value from 512 to 1. Let me go back to an image view here, which is more appropriate given that it's a 2D data set. Now, what if I want to bin this acquisition? And bin for me right now means pooling pixels. So right now I'm each individual physical pixel on the chip is getting read out separately. What if I wanted to maximize my signal to noise ratio at the cost of some spatial sampling information? Or I guess I should say maximize my signal. I'm gonna just capture as much signal as possible by pooling and measuring the electrons in multiple pixels in one readout cycle. So let me go up to acquisition setup, and I can either do this or I can click these gears here and change the acquisition. So let's do the simplest binning mode, at least to set up, which is full vertical binning. And what that means is we're going to pool the pixels in a full vertical stripe along the sensor. So each column will be read out as one value. So let me do that now, and all I had to do is change the readout mode to FVB. You can see in the FVB options there's not much to change other than horizontal binning, which will then further bin in the horizontal direction. So let's see what happens when I do this. Let me acquire the image or acquire the data. And now I have what looks like a barcode because it's now one-dimensional information where I have one cross-section or one trace that symbolizes the intensity across each column of the sensor. And let me view this more appropriately as a 2D view. There's not a tremendous amount of information here for me. It's not a spectrum. It's just simply an image that's been summed along the vertical direction. And that's across the entire sensor as well, the whole field of view of the sensor. So let me go back to a image readout. Image readout. And view the image again. You can see it's now still in the 2D view, so I get a series of cross sections. Let me go back to an image here. Right now I'm using the Solace imaging version because I'm not connected to a spectrometer. So if you're connected to a spectrometer, you'll see down here there'll be additional GUI elements that speed up some of this. Now the question is, what if I wanted to do a more involved binning scheme? Well, let me go to acquisition setup, and I have to start an image mode and go to the binning tab up here. If I click FVB, this binning tab disappears. So let me go up to image, and I can enter my ROI or region of interest, which is partial chip readout. And then I can enter arbitrary binning as well. So let me start with a custom region of interest. Say I just wanted to vertically bin in the center of the chip. I can either draw onto the image, and I could pull this around and say I just want this part of the sensor to be read out. Apply that. And it will enter the pixel numbers for me, or I could enter these myself manually. If I said I want to go from pixel 100 to pixel 400 or something like that. So let's just see what happens when I do this. I'm just going to set this OK. Take an image. And now you can see I've just read out the center of the image. Why would I want to do this? Well, this is a lot faster. I've got less pixels to digitize. And if I digitize fewer of them at the same rate, I can do I can do my measurement faster. And that will show up, if I go to acquisition setup and I set up a kinetic series, you can actually see the time change that this is going to manifest as. So I'll go to kinetic series. Let's set to 100 frames. And you can see with my ROI, I'm at 21 hertz. If I go back to here and go to full, it'll recalculate that and it'll be 18 hertz. so I'm going quite a bit faster here. Let's go back to my custom binning, and I'm going to go back to a single image. Oops, single image. Now let's bin within that image. So let's go custom here because I want to do full vertical binning. These presets are all square binning, so larger and larger super pixels. Maybe just real quickly, let's see what that does. If I go to 16 by 16, what it's going to do with this current setting is it's going to read out just this part of the chip, and then within that chip, it's going to take little chunks where 16 by 16 pixels will be pooled together, and we'll get one measurement with lower spatial resolution, but a much higher signal per pixel. So let's see what that actually works out to. Yep, much lower spatial resolution, but all of a sudden I have significantly higher numbers of counts. You can see my Y scale has changed here, my color scale, where I'm getting tens of thousands of counts per pixel rather than a few hundred. And you'd expect naively about a 256-fold increase in signal based on 16 by 16 binning. So let's go back to the acquisition setup. And again, my goal is to vertically bin here. So let's go to custom, where I can enter arbitrary binning. And horizontal, if you float, it'll tell you which is which, horizontal and vertical. So I'm going to do 1, and I want to do the whole ROI. So let's just throw in a high number, and it'll reduce it to the maximum height of that ROI. So let's take an image. And again, it looks like a barcode because I'm just doing 300 pixels across this way. If I want to view it in a more appropriate format, I'm going to go to 2D, and I have my ROI as basically a spectrum. This will, of course, if you're doing a spectral measurement, this will mean a lot more than it does now. Right now, we're just looking at the intensity of that image in my test rig here, viewed as a 2D slice, summed across the vertical direction. So let's go back. I hope that made it clear. If you have questions, again, feel free to send me an email at a.wise@andor.com. But let me go back here and talk about a little bit more of the custom stuff, or a little bit more of the advanced options. So first, retain absolute coordinates in dataset. What does this mean? I mean, you're welcome to try it yourself, but what this does is, if I unclick this and I say don't worry about the absolute coordinates, and that's absolute coordinates of my ROI, what will happen is it will read out the middle 402 minus 115, 300-ish pixels, and it will say, okay, this is pixel 1, this is pixel 2, this is pixel 3, and it'll say whatever the first pixel I read is my start of my data, whatever the last pixel I read is the end of my data. So let's see what happens if I unclick that. And just to give you a quick heads up here, you can see how my data set is floating in the middle of this view, just kind of as it fits in this chip. So we're retaining the coordinates here. If I unclick that like I just did and redo the acquisition, now all of a sudden my data set is only the pixels that I have selected. So before, I'm kind of padding the measurement with zeros or NANs or something on either side to remind myself that this is a section from the middle of the chip. So let's go back here. I'll re-enable that. Now what if I do binning in software? It's going to be hard to see this, and maybe we can get it to do what it's going to do to demonstrate the difference real quick. But right now we're doing the binning in hardware. What does that mean? The binning is happening on chip, so we're actually physically marshalling photoelectrons or electrons that were generated by the absorption of photons together into little corrals. We're physically pooling them by pushing them with voltages into a single register and then reading out that register in one shot. So the advantage is that I'm reading out this whole column with one read. That means I only get the read noise once. If I switch this to binning in software, it's not as fast because now we have to read out each pixel, and it will add those numbers together after digitization in memory, in the computer, not in the chip or not on the chip. The advantage of this, I've just given you a bunch of disadvantages, which is to say higher noise. The noise will be the square root of 304 times the read noise. And it will also be 304 times longer to digitize this. What is the advantage? The advantage is that now I'm not limited by the 16-bit ADC for the whole column anymore. I'm going to digitize, and I can have up to 2 to the 16 counts per pixel and then add them together in software in some floating point number and get some arbitrarily high number for my purposes. And again, if you have more questions, feel free to send me an email at a.wise@andor.com or visit the Andor website for more information.